Lesson: Handling Imbalanced Datasets in AI. Handling imbalanced datasets is a critical challenge in the realm of artificial intelligence, particularly within the field of machine learning. Imbalanced datasets occur when the classes in a dataset are not represented equally. This imbalance can significantly skew the performance of models, leading to biased predictions that do not accurately reflect real-world scenarios. In practice, this often manifests in applications such as fraud detection, medical diagnosis, and churn prediction, where one class may be significantly rarer than the other. Addressing this imbalance is crucial for developing models that are both accurate and reliable. One of the primary strategies for handling imbalanced datasets is resampling. Resampling techniques aim to adjust the class distribution within the training data. Two widely used methods in this category are oversampling and undersampling. Oversampling involves duplicating instances of the minority class to balance the dataset. A common approach is the synthetic minority oversampling technique, which generates synthetic samples for the minority class by interpolating between existing instances. This method can be implemented using Python's Imbalanced Learn library, which provides a straightforward interface for applying SMOTE. On the other hand, undersampling reduces the number of instances in the majority class. This can be done randomly or through techniques like Tomek links and cluster centroids, which aim to retain the most informative samples. While these methods are effective, they also come with trade-offs, such as potential overfitting in the case of oversampling or loss of valuable information with undersampling. Beyond resampling, cost-sensitive learning is another vital approach for managing imbalanced datasets. This technique involves modifying the learning algorithm to penalize misclassifications of the minority class more heavily. By altering the cost matrix, models become more sensitive to the minority class, thereby improving their predictive performance. For instance, in support vector machines, different penalty parameters can be assigned to each class, allowing for a more balanced decision boundary. Similarly, decision tree algorithms can incorporate cost-sensitive pruning to maintain a focus on minority class predictions. Implementing cost-sensitive learning requires a deep understanding of the problem domain to set appropriate costs, but it can significantly enhance model performance on imbalanced data. Ensemble methods provide another robust strategy for handling imbalanced datasets. These methods combine multiple models to improve predictive accuracy and robustness. Bagging and boosting are two prominent ensemble techniques. Bagging, or bootstrap aggregating, involves training multiple models on different subsets of the training data and aggregating their predictions. Random forest, a popular bagging technique, can be modified to handle imbalanced data by adjusting the class weights or sampling strategy. Boosting, on the other hand, focuses on creating a sequence of models where each subsequent model attempts to correct the errors of its predecessors. Adaptive boosting and gradient boosting are commonly used boosting algorithms that can be adapted for imbalanced datasets by incorporating cost-sensitive learning. These ensemble methods are particularly effective as they leverage the strengths of multiple models to counteract the effects of class imbalance. In addition to algorithmic adjustments, evaluating model performance on imbalanced datasets requires careful consideration. Traditional metrics such as accuracy can be misleading in imbalanced scenarios, as models may achieve high accuracy by simply predicting the majority class. More informative metrics include precision, recall, and the F1 score, which provide insight into the model's ability to correctly identify minority class instances. The area under the receiver operating characteristic curve and precision recall curve are also valuable for assessing model performance, offering a comprehensive view of the trade-offs between true positive rates and false positive rates across different threshold settings. A practical case study illustrating these concepts can be found in the healthcare sector, specifically in the early detection of rare diseases. One such example is the prediction of Alzheimer's disease using machine learning models trained on imbalanced datasets. Alzheimer's disease is characterized by a long preclinical phase, making early detection crucial for intervention and treatment. Researchers have employed various techniques to handle the imbalance in datasets used for Alzheimer's prediction. For instance, a study by Liu et al. Explored the use of SMOTE and random forest to enhance the detection of Alzheimer's in its early stages. By oversampling the minority class and leveraging the robustness of ensemble methods, the researchers achieved significant improvements in predictive accuracy and recall. This case study underscores the importance of employing multiple strategies in tandem to address the challenges posed by imbalanced datasets effectively. Another notable example is in the financial industry, particularly in fraud detection. Fraudulent transactions are rare compared to legitimate ones, resulting in highly imbalanced datasets. In this context, cost-sensitive learning and ensemble methods have proven particularly effective. A study by Sahin and Duman investigated the use of cost-sensitive decision trees and ensemble models for credit card fraud detection. By incorporating higher penalties for misclassifying fraudulent transactions, the models demonstrated improved performance in identifying fraud while maintaining a low false positive rate. This highlights the necessity of adapting traditional models to account for the unique characteristics of imbalanced data in real-world applications. The practical implementation of these strategies requires familiarity with various tools and frameworks. Python, with its extensive library ecosystem, provides numerous options for handling imbalanced datasets. Libraries like scikit-learn offer built-in support for cost-sensitive learning through parameter tuning and custom loss functions. The Imbalanced Learn library, mentioned earlier, is a valuable resource for resampling techniques, providing intuitive methods for implementing SMOTE, atomic links, and other approaches. Additionally, platforms like TensorFlow and PyTorch allow for the customization of deep learning models, enabling practitioners to incorporate cost-sensitive learning and resampling directly into their workflows. In conclusion, handling imbalanced datasets is a multifaceted challenge that requires a combination of resampling techniques, cost-sensitive learning, and ensemble methods. Each approach offers unique advantages and trade-offs, and their effectiveness is often enhanced when used in combination. By understanding the underlying causes of imbalance and leveraging appropriate tools and frameworks, practitioners can develop AI models that accurately and reliably reflect real-world scenarios. As demonstrated through case studies in healthcare and finance, addressing dataset imbalance is essential for unlocking the full potential of AI applications and ensuring their success in diverse domains.